It's very humbling to realize that of everything we can touch and see, the planets and the galaxies make up just 5% of the universe, and the rest is a complete mystery.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
My guest today is Klaus Honscheid, professor of physics at The Ohio State University College of the Arts and Sciences. He is a member of the Dark Energy Survey and the Dark Energy Spectroscopic Instrument, DESI, both of which we'll discuss here this afternoon. Dr. Honscheid, welcome to Voices.
Yeah, thank you for having me.
Well, so dark energy is in the title of both of those collaborations, and I think maybe we should start with a definition of what dark energy is.
Yeah, we're very creative in our names, aren't we? Des and Desi. It's a shame. Anyways, so what happens when these experiments were conceived in the early 2000s, a couple of years before, we noticed something completely unexpected in the universe. That the universe, we all thought, would, expand, but gravity is everywhere, pulling stuff back together. So eventually gravity would take over and the acceleration would at the minimum slow down, if not reverse.
The acceleration of the universe.
The expansion,
right? Yeah.
The overall expansion. But then two teams in 1998 looked at this and actually measured it, and you have an idea that you should verify it. And they found the exact opposite. Instead of slowing down, the expansion was accelerating. The universe was growing faster and faster. We have no idea what it is, but we knew or know there must be something in every empty bit of space that's actively pushing the universe apart. If you don't know what it is, at least you have to give it a good name, so we call it dark energy. And we are still at this point. We don't really know what it is. All we have accomplished over the next 20 years until today is to describe it.
And dark energy is different from dark matter, yes?
They are totally different things. Dark matter is also an invisible substance in the universe, and we knew about that since the 60s and 70s. And we knew it because we looked at how galaxies, not ours too, but we looked at other ones, how they rotate. And we noticed that the stars at the rim of the galaxies moved so quickly that by standard physics, they would just fling themselves out of the galaxy. They would just disappear. But they don't. So the only answer is that there must be something invisible with an enormous mass that covers the entire galaxy that holds stuff together. And again, we have not yet detected the particle nature of this, so we gave it a good name. We call it dark matter. So dark matter is, we believe, related to particles in one way or the other. Again, we don't have the particle identified. It acts gravitationally. It holds the galaxies together. In fact, it holds the entire universe together. It's the scaffolding of the entire universe. The galaxies and the stars we see form in large, we call it a halo, large amounts of dark matter, because there's a lot of gravity, the gas comes in, it compresses, it ignites, it forms stars. So dark matter is critical for forming the universe as we see it. Dark energy does the opposite. Instead of pulling stuff together, it tries to expand the space and push everything out. So they have a similar name, but they are very different things. One, we believe, has in one way or another a particle nature. Dark energy, on the other hand, is more an intrinsic property of space itself.
So I know that matter and energy interact or relate with each other. Do dark energy and dark matter interrelate in any way?
I don't want to give you a complicated answer. The obvious answer is we don't know. In our basic understanding, the answer is no. But since we're beginning to see features of dark energy that we don't understand or can explain, there are people out there, theorists, that come up with coupled dark sectors where dark energy and dark matter do interact. But these are just attempts to explain the current set of data. and not necessarily adopted overall accepted theories or so. Yeah, the basic idea is no, they're not connected.
So we don't yet have the Einstein for dark matter and dark energy.
No, that's what we need. We need somebody to put the data we are collecting together and come up with the model that describes it in a way that explains it all. Yes.
Let's talk about the Dark Energy Survey. What is this survey?
So the Dark Energy Survey was designed as basically the largest digital camera at its time. We put it on a telescope in Chile, and we were taking images of about 1/8 of the entire sky. And the idea was to basically image these galaxies and the distribution of the galaxies to the best possible way. And I think I said, I don't remember, that dark matter is invisible. But it's also the dominant matter in the universe. So if you want to learn about the expansion of the universe, you need to know where the dark matter is. So you need to take an image of the dark matter. But how can you take an image with a camera?
You just anticipated my next question.
Okay, so here we have to bring in Einstein, who in his general relativity came up with the insight that space and space-time itself is actually directly connected to whatever stuff, I use that term colloquially, is inside the space. Matter, dark energy. And the material, the matter, curves space, and when space is curved, it determines how matter moves through it. So what happens is, if we have light from a galaxy far away, traveling to our telescope and we take an image, if there is a large cluster of galaxies and a surrounding even larger halo of dark matter which we don't see, the light that travels through this, it's like going through a deep gravitational. The light thinks, oh, I'm going in a straight path, but when you look at it, it's actually bent. And we can see this in our telescopes. So what we do is we measure the distorted images of these background galaxies, and we measure this precisely, and then we can reverse engineer the mass and figure out how much mass was necessary to generate this distortion. And while we can't see dark energy, this way we can map its distribution. And that's what the Dark Energy Survey does.
Mm-hmm. What has the survey revealed thus far?
So the survey has made the largest maps of dark matter in the universe, and it has condensed the data to statistics that allows us to compare the distribution to the expectation. Cosmologists have a standard model that was developed over the last 20, 30 years that explains what we see. It doesn't explain what is dark energy and dark matter, but it explains how these quantities affect the visible universe. And we did measurements and compared the distribution of these galaxies to the prediction, and that came out to be close enough to say, okay, fine. So basically you have to think of the universe as a constant tug of war. You have gravity trying to pull everything together, and you have dark energy trying to push everything apart. And that went on for 10 billion years. And the current, let's call it shape of the universe, depends on the outcome of this tug of war. And our model allows us to basically predict how it should look like. We know the relative amounts, and we can say, given all of this, we should have a certain amount of, pardon the non-scientific term, clumpiness in the universe. And we can measure that. And it turns out that the universe is about as clumpy, meaning the galaxies are clustered at more or less the right amount. So that is all encouraging. It means two things. It means that this model that includes about 68 or so % of dark energy and 27% of dark matter describes the history of the universe very well. That's the good news. And the bad news is it all matches. So we don't get a hint where it breaks down. So we don't have a hint yet to what else could be going on. So it's a fascinating experiment with incredibly strong results, but it just confirms, which is, okay, we have to be excited that it just confirms what the model is, but of course, it would also be nice to see something that gives us a hint of there's a new thing going on.
This is how science works, of course.
It is, yes.
What role does the Dark Energy Spectroscopic Instrument play in the survey or otherwise?
Yes, so DESI came a little bit later, and it approaches the same questions differently. A camera can take images of the sky. That gives you basically a two-dimensional view. DESI gives you a three-dimensional map.
Interesting.
So if you see the universe in 3 dimensions and the map is accurate, you can slice it in a different way. You can basically slice the universe into, I need to maybe go back a moment. Light takes some time to reach us from distant galaxies. So looking back at distant galaxies is basically like looking back in time. So if we take our map of the universe and look at distant galaxies, we are looking at the universe how it was billions of years ago. So by doing this in 7 slices, we get 7 measurements of the evolution of the universe. And DESI enables this. So it's a spectroscopic instrument. That means we take the light from every galaxy, break it into the wavelength, instead of just an image. And when light travels through space, because space is expanding as the light is traveling, it stretches the wavelength. So if you emit blue light a billion years ago, that is a wavelength of a certain wavelength, a few hundred nanometers. But when it reaches us, since space is now expanded during the time it traveled, it comes here as red light. So we call this a redshift. And by measuring the change in wavelength, we can measure this redshift with a spectrograph. And then there is a law called Hubble's law that tells us that the distance to the galaxy is related to the velocity. The further the galaxy is away, the faster it moves away from us. We can use this to convert the shift in wavelength into a distance. So by doing this, we have 3-dimensional data points. What DESI brought new to the world is it can do this extremely efficiently. It can take 5,000 of these spectra at the same time, and it can reconfigure as you move to a different position on the sky. The galaxies you want to look at are somewhere else. So DESI can reconfigure and target different galaxies within a minute. That is, in past version of similar experiment, it took half an hour or so to do the same. So that is a major improvement. And when we do this, we can measure this evaluation or the expansion history of the universe. So that's fine. But it only gives us information if there's anything we can measure. And for that, we were fortunate that there is something in nature that is a known calibrated physical standard. Early in the universe, it started with the Big Bang. It then expanded, we call that inflation. And then about 400,000 years later, this primordial plasma cooled down enough so atoms can form. That means radiation is no longer trapped and it escaped. We see that today as a cosmic microwave background, and we know about this. It's one of the strongest arguments for the Big Bang. But something happened in this early plasma. There was something like action and reaction. There was gravity pulling stuff together and all the radiation whizzing around, knocking everything back. And this is the same that happens when you produce a wave. So we had sound waves in the primordial plasma. So these sound waves were there, and they expanded until the photons disappeared 400,000 years later, and they left an imprint. So we have a measure in the early universe where we know the exact physical size. And what we have shown over the year is that this imprint is still visible in the distribution of the galaxies today. If you just look at the most likely separation between galaxies, there's a slight enhancement at that distance. So we measure this over different periods or areas in the universe and compare it to the model. And that's where DESI found it's close to the prediction, but it seems to deviate in particular in the younger universe. And that's when the collaboration started to use different models, including giving up on the cosmological constant, the dark energy explanation we have in our standard model. And if it's not constant, and we allow it to vary, not knowing why, but just putting it mathematically to describe it, it's a much better fit to the data. So the data prefer a varying amount of dark energy in direct contradiction to Einstein's cosmological constant. And that's fascinating. So we were really excited when this came out.
So what does that mean? Does that mean we have to throw away Einstein?
No, of course not. This general relativity theory is incredibly brilliant. But it means that it might need corrections. It might need, when we announced these results, the buzz in the community was like incredible. Every news outlet picked it up. And since we did this in the spring, there are now 1,700 scientific citations. Citations are the currency in our field, and 1,700 is a huge amount. Most of them are from theorists trying to explain what it is. So there are about 1,700 different theories to explain what this could be. Or let's say 1,700 trying to explain what we did wrong. So yeah, that's okay. So there are different ideas out there. It would become way too technical to try to explain this. Some of them are easier to grab, and that means that when you go to cosmological scales, general relativity just is not the correct description of gravity. Now that is possible, maybe not the most likely, but it is a possibility. As an experimentalist, I'm much more worried about the other side. This data is great and we are excited, but in all of science we have seen so many 3 sigma effects, that's about the significance of the result, disappear with more data, with better analysis, with more careful look at the systematic uncertainties. So we want to be very careful. We are excited, we presented the data as we see it, but we are not claiming that we broke general relativity. So we just say there's a very strong hint that dark energy is evolving, and we need to see what the future will tell us about this.
So I'm curious to know what that might mean, that dark energy can evolve. Evolve into what?
It's hard to grasp this since we don't really know what it is. So what it means in our observation is that it gets weaker now. So this push to keep the universe apart or to stretch the fabric of space is weaker now than it was 7 billion years ago. Why? We don't know. If it is changing, that opens up questions. Will it change more? Will it change to the extreme that it becomes so weak that it maybe flips sign and becomes attractive? Or will it change direction again and becomes stronger and stronger? We don't know. We will not know how to answer these questions until we have an actual understanding of what dark energy is. So these questions, fascinating, but the answers have to wait.
What's your role with DESI?
So I'm in this interesting position that I'm a physicist, but at heart I like to build stuff. Putting these things together, the DESI experiment is an incredibly complicated instrument. We use 5,000 tiny robots to position optical fibers to an accuracy of 3 microns. These fibers have a diameter of 100 microns. That's about the diameter of a human hair.
Ooh.
And we position them accurately that we can point them to the sky and collect the light from a galaxy that was emitted 10 billion years ago. That's a fun challenge to solve. And we do this 5,000 times in a minute to get our throughput. So building this and orchestrating this dance is just an incredible. I was so lucky to be in a position to work on this. So I enjoyed this very much. So I'm currently serving as the instrument scientist for the collaboration or co-instrument scientist with one of my colleagues. So I'm responsible for the operation of the instrument and the survey operation and make sure that things keep working. Yeah.
Where is DESI located? It's not here in Ohio State.
No, DESI is located on Kitt Peak at Kitt Peak National Observatory. That's a mountain about an hour west of Tucson in Arizona.
And how many other scientists or institutions are part of this project? It's more than just Ohio State.
That is correct. The amount of work, A, to build it, B, to run it, and C, to do all this analysis is something that can only be done in a large collaboration. So DESI is an international collaboration across the world with it's hard to get an accurate count because people, if you take the active people, it's maybe 600. So it's a large number.
It's very large, yes.
Yes. And if you go through, you need everybody. You need all of them.
How does one manage a scientific project like that?
So that is, I think, the best way to say this is you go into this. You cannot just say, okay, I start from scratch here, 600 people, let's work together. There's a huge background in particularly the particle physics community in running large experiments. Many of these people joined Cosmology for DS and DESI. And the people who manage the projects are all at national laboratories with a strong background in project management. They're all physicists and scientists, but they have experience and over the years for larger and larger projects to manage this. And we are very fortunate that we get substantial funding from the national government. And they make sure we use the federal funds, the taxpayers' money, as I say, wisely. So there are very serious reviews. You have to do very serious accounting and demonstrate that you make enough progress. Yes, so that is mostly during the construction phase of the project to make sure that you build it on schedule and on budget. And for both of these, our leadership was incredible, and we managed and we actually delivered. Yes.
How'd you end up in this role as the instrument scientist?
You see, the combination of being a physicist with a strong tendency to do engineering work is uncommon. So there were not too many other people like me around. And I enjoy building and operating this stuff. And I like doing this. And other people like this too, but they also had a strong interest in simulations or whatever aspect of the experiment. So basically, it just became naturally. I had asked my colleagues, but enough talent to do this, and I wanted to do this, and the opportunity was there. I'm just lucky.
Where did that come from? Where did you learn this ability?
Oh, yeah. Let's say it this way. When I did my thesis way back in Germany, in Bonn, I went to my thesis advisor. I knew I wanted to work with him because he was a brilliant and incredibly friendly person. And I told him, I want to work with you, but I want to do this. And I told him what I wanted to do, and that was building some piece of equipment for an experiment we were doing at this time. And to his credit, and I'm forever grateful, he said yes. He had no idea about computers and electronics and what I was doing, but he supported me, and it was incredible. It was a lot of fun. And it worked out in the end, yes.
So why physics? Why aren't you an engineer?
Sometimes you have to make choices in life, and this one is maybe, I don't know if I should confess this, but it was a matter of convenience. In Germany, not every university offered engineering, and my home university, where I wanted to go, had a very strong physics program, and I decided, why not become a physicist? That's how it happened. Yeah.
So it's unusual for physicists to be, tinkerers? Is that unusual?
Let's say it this way. I wish there were many more. And there are enough of us around to make this, build these instruments. And I think all of us who do this enjoy it tremendously. But it's certainly true that in this field, the vast majority is focusing on the analysis of the data. That's true, yes.
So as we record this, just this past week, you were invited to deliver the Biard Lecture. Could you tell us, first of all, what this lecture is, and what did you talk about then on Wednesday?
So we are here at Ohio State. We are very fortunate that for 20 years we have a Center for Cosmology and AstroParticle Physics. It goes by the name CCAP. CCAP has been incredibly instrumental to get our groups into both of these experiments. And then a few years after it was founded, we got support from the Biard family, and they endowed a lecture series. And for 16 years we do this now, and for the 16th version of it, the one from last Wednesday, they, for whatever reason, asked me to present what we have done over the last 20 years with both DS and DESI, and what we have learned, and what are the interesting things about dark energy these days.
And what we've been talking about here, or did you talk about something else?
No, I think it was very similar to our conversation here. I tried to explain to the audience how we got to know about the expansion of the universe, because you don't see it if you just look up. How we got to know about dark matter, and then how we got to know that there must be something like dark energy. And then it's very humbling to realize that of everything we can touch and see, the planets and the galaxies make up just 5% of the universe, and the rest is a complete mystery. So, well, we see it as a challenge, so we got to work on it. And so I try to explain this in the lecture and try to present them how both DES and DESI are working actively to shed some light into these 95%. Yeah.
Cosmology deals with time scales of
Yes.
billions of years, distances that are almost unfathomable, unimaginable. Has working at those scales changed the way that you think about human life or human history?
I don't think so. It is so different, and we're not just talking a factor of 2 or so, we're talking, I don't know how many orders of magnitude, so I don't think so. What gets me every time I look at this and drive to the telescope is how grateful I am that we get to do this. There's no application. Dark energy is so tiny. If you would convert it, I made that joke at the lecture, if you would convert it into food calories, it's 1/1,000,000th of a calorie. So it's not like this will be the energy source of the future. There is really no application. And still, I think, as a civilization, curiosity needs to be supported, and that's what we do. We look at things that are not affecting your daily life, but they are still so fascinating. And as I said, I'm really grateful that we can do this.
So what's next for Klaus Honscheid?
Klaus Honscheid, you don't see me since this is a radio blog, has gray hair. And
Just like your host.
And so, as I indicated, we have this hint in the data, and on the experimental side, it now requires continuing effort to get more data, to look at it differently. And the field is fortunate enough to have 3 major initiatives starting on this right now. My DESI experiment will turn into what we call DESI 2. Again, we are not very creative in our naming schemes. And this will run until the middle of the next decade, basically refining these measurements, hopefully to the extent that we have a clear discovery. And I will make sure before eventually I stop being at OSU that this goes underway and make sure that the instrument keeps running and hopefully find enough of these physics tinkerers that we mentioned that enjoy what I've been doing so they continue.
Klaus Honscheid, thank you very much.
Thank you for having me.
Voices of Excellence is produced and recorded at the Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Voices of Excellence is produced by Doug Dangler. I'm Jen Farmer.